So we're going to do a brief review of resting membrane potential. So resting membrane potential is basically based on the fact that the plasma membrane is selectively permeable. And so what ends up resulting is a membrane potential or difference or separation of charged particles across the membrane. And we define that as voltage, which is electrical potential energy that results when we take oppositely charged particles and separate them across the plasma membrane. So in our cells, ions are the charged particles that we separate across the plasma membrane. So what we see is that a typical cell in the body has a resting membrane potential anywhere from -50 to -90 millivolts. And so what that means is if we had our cell, generally we're going to have a more negative charge on the inside of the cell versus the outside. Okay, so if we were to measure the charge right on the inside of that plasma membrane, we would see that it's resting at about -50 to -90 millivolts. Now this difference in charge only exists at the plasma membrane. If you go inside the cell, you're going to see that the charges are neutral. So the charges, the amount of positively charged ions and negatively charged ions are going to even out. So our electrical charge is going to be actually neutral inside the cell and neutral outside the cell in the extracellular fluid. So this potential only exists at the plasma membrane. Now, how does this happen? Well, a couple different things have to come into play. So our key players here are going to be potassium and sodium. Okay, now we do have negatively charged chloride ions that don't really play a significant role in maintaining resting membrane potential or establishing resting membrane potential. And we also have these positively charged negatively charged proteins that also don't really play a significant role either because they can't make their way through the plasma membrane. So our key players are potassium. It's important to note that potassium is in higher concentration inside the cell. So we have a much larger concentration of potassium inside the cell than outside. And so we have leakage channels that are going to be embedded in the plasma membrane. And these are open all of the time. So they are slowly allowing potassium to leak out of the cell down its concentration gradient. Okay? As positively charged potassium ions leave the cell, it ends up creating a negative charge inside the plasma membrane. Okay? In fact, so much so that this negative charge that is created inside the plasma membrane ends up eventually attracting potassium back into the cell through the electrical gradient that is established by the slow leakage of potassium out of the cell. At a voltage of -90 millivolts, the concentration and electrical gradients of potassium balance. So what does that mean? We have a concentration gradient of potassium pushing potassium out of the cell, and we have an electrical gradient for potassium wanting to move potassium back into the cell. Okay, and at a voltage of -90, these two concentration gradients are equal. Now, we also throw in a little sodium because sodium plays a role too. Now, sodium is in higher concentration extracellularly, so outside the cell, but it also has sodium leakage channels as well. So sodium is going to want to diffuse into the cell. I know on this picture this is showing potassium, but we can also use this to show sodium as well. Let's just pretend that this is a sodium leakage channel. So sodium is going to diffuse into the cell down its concentration gradient. And now we have an addition of positively charged sodium ions. So our initial membrane potential of -90 that was established by potassium has now just been increased through the addition of positively charged sodium up to -70 millivolts. Okay? Now, what is interesting is that these leakage channels are open all the time. So we have constant diffusion of sodium and potassium. And if this was all that we had, we would eventually reach equilibrium where we would reach electrochemical equilibrium on both sides of the plasma membrane. But that's not what happens, and that's not what we need. We actually need to have voltage across the plasma membrane. So we end up throwing in sodium-potassium pump. So sodium-potassium pump is active, so we do require not only passive diffusion of ions, but also the active pump of sodium-potassium pump to help maintain our resting membrane potential. So sodium-potassium pump is continuously removing sodium from the cell and helps to maintain our resting membrane potential. So if we look at our different steps here, the plasma membrane is much more permeable to potassium. So potassium is constantly leaking out through the slow leakage potassium channels. Okay. Now, we also have leakage sodium channels, and sodium is going to diffuse into the cell down its concentration gradient, giving us a resting membrane potential of -70 millivolts. Now, we need to have some way to keep sodium in a higher concentration outside the cell and potassium in a higher concentration inside the cell. And that's the role of the sodium-potassium pump. Because if, again, those ions were just left to leak through their leakage channels, they would eventually reach equilibrium. So the sodium-potassium pump is here, and it's going to throw out 3 sodium ions to maintain this concentration gradient of sodium, where sodium is in higher concentration outside the cell. And it's going to pump in 2 potassium ions to maintain the fact that potassium is in higher concentration inside the cell. So it enables us to maintain this concentration gradient so that our leakage channels create movement as well. But it's important to remember that with the resting membrane potential, we have both passive diffusion here, passive diffusion here, creating a resting membrane potential, but then the resting membrane potential is maintained using active transport processes that we see with the sodium-potassium pump.